In this video, we're going to look at the normal distribution. So we're going to find probabilities of the standard normal distribution, talk about those of a non-standard normal distribution. Then we're going to kind of go backwards through the process and find the value of a normally distributed variable that will produce a specific probability. So to get started, we need to think about histograms. So looking at a specific example of one we looked at in a previous video, the weights of bags of chips. We talked about that this histogram right here is special in the fact that it is symmetric. It looks like it's kind of the biggest in the middle and it tails off at the end. And this is in fact what we call a normal distribution. But as it is right now is not how we're going to think about normal distributions. So instead, what we could do with this example is we could make the groups are how we divide the data here. And we could make them smaller and smaller and smaller. So I looked at another histogram here where we made the group size 0.1 instead of 0.2. We had twice as many groups. And we can see that our histogram, again, sort of looks like this bell-shaped curve. But the idea is that if you kept on making them smaller and smaller, right, did 0.05 and 0.01 groups or something, we would eventually get this normal distribution. So here, if we think about this normal distribution is here in the histograms. And if we actually made those groups smaller and smaller, we would get the exact histogram. So if these little bars were really, really small, we would get exactly this normal distribution. But we're not going to draw all those bars. We're just going to say this is our distribution. So remember what the histogram tells us. The area of a bar, so here the area is 0.29. It's from that value right there. That is the area of the bar relative to the area of all the bars. So that is 29% of the area is in that bar. And we're going to think about area of a chunk of this histogram and talk about what's the percentage of that. That's going to be basically what we're going to do this entire video. All right, so here is our curve that we're looking at. That curve is called the normal distribution, and it's going to be related to histograms, except that we're not really going to be drawing the bars. We're just going to be thinking about this kind of continuous variable on the bottom here. We'll see some examples of that in a second. So a normal distribution has two main properties. That's going to be the same for all normal distributions. There is a strong central peak. That means the frequencies of the data point near the center, or the average, are increasingly higher than those away from the center. And it tails off on both ends. So it's high at the center and tails off at both ends. Also, we need that the distribution is symmetric. So if you would draw a line down the middle, that'd be a mirror image on the left and the right. So those two things kind of define what a normal distribution is going to be. And note that because of this shape, we will have that the mean is in the center, the median's in the center, and the mode are all at the center at the same value. And we're going to call this mean mu. This is the Greek letter mu, and that's going to represent the mean. So the mean is always going to occur at the special value mu. The difference from one normal distribution to another is really going to be in the standard deviation, which we're going to denote with sigma. So we can have different normal distributions, right? You can have a strong central peak in a lot of different ways and be symmetric. Doesn't have to be centered at the same kind of spot either. All those are normal distributions, but they all look kind of different. It's going to be the standard deviation that's really the difference between them. So quick note that we use mu and sigma instead of x bar and s. And the reason for that is because we're actually looking at the entire population and not just a sample. This is the population mean and population standard deviation. That might be a little bit too technical. In this case, let's just say that we're using these letters now instead of the old ones. All right, so our mean, which is the same as the median and the mode, is mu, standard deviation is sigma. All right, so what's really special about the normal distribution is that we really understand what is the area of these different chunks of a standard deviation. In fact, it's known that 68% of the data in a normal distribution lies within one standard deviation of the mean. So we talked about within one standard deviation of the mean in the previous video. So we're looking at, here's the mean, and we're looking at if we subtract a standard deviation and add a standard deviation, looking at that range, and we're saying that the area under that normal distribution corresponding to that range is 68% of the total area under that normal distribution. And that's going to be exactly the case for any normal distribution. If we looked at within two standard deviations, 95% are going to lie within two. So if you looked at the area within two standard deviations of the mean, that's going to be 95% of the total area. And then finally, 99.7% lies within three. So almost all of the area is going to be within three standard deviations of the mean. Now, there's still a little bit left here on the outsides, but that's only going to represent 0.3% of the population. It's not a huge amount. And that's kind of the main purpose of this normal distribution, is that we get almost everything within three standard deviations of the mean, almost everything within two standard deviations of the mean, really. All right, we're going to call this fact the 68, 95, 99.7 rule. All right, now let's use that rule and kind of understand it in a real world example. So heights are a good example of thinking about normal distribution, because if you think about a large group of people, the heights of people are normally distributed. Most people are kind of an average height. And as you get further and further away from that average, you get less and less people who are that height. So yes, there are people who are 7'5", but it's not a huge chunk of the population. Most everybody's going to be about the mean. So the height of a large group of people is normally distributed with a mean height of 66.5. So that means that mu is 66.5. And a standard deviation of 2.4, that's going to be our sigma. Find and interpret the intervals representing within 1, 2, and 3 standard deviations of the mean. So within one standard deviation of the mean, we're saying we're doing mu minus sigma to mu plus sigma. That's going to be 66.5 minus 2.4 and 66.5 plus 2.4. And that interval is going to be 64.1 to 68.9. So that is the interval. What does that represent? That says that 68% of people in this large group are within 64 point, or are between, I should say, are between 64.1 inches tall and 68.9 inches tall. Within 2 standard deviations, so we're looking at mu minus 2 sigma to mu plus 2 sigma, that is 66.5 minus 2 times 2.4, and 66.5 plus 2 times 2.4 is going to be 61.7 and 71.3. And what does that represent? This says that 95% of people are between 61.7 inches tall and 71.3 inches tall. And finally, we can do 3 standard deviations, mu minus 3 sigma, mu plus 3 sigma. That's 66.5 minus 3 times 2.4 to 66.5 plus 3 times 2.4 is going to give us a 59.4, or sorry, 0.3, and 73.7. And that means that 99.7% of people are between 59.3 inches tall and 73.7 inches tall. And this is our 68, 95, 99.7 rule. All right, so now we're thinking about, instead of relative frequency, instead of this, we're going to think about probability. So let's think about how these are related again. So relative frequency is, let's say that the relative frequency that a person has red hair is 0.03. What that means is that 3% of the people in our sample have red hair. So instead, we could think about that as the probability that a person in our sample has red hair is 3%. Those things are very much aligned. So the relative frequency of a histogram is the area of the bar relative to the entire area. We talked about that in the first slide. So with normal distribution, we can represent probabilities with area under the curve. So the next few slides are just going to talk about what does that area represent, and then we're going to spend a little bit of time finding those exact probabilities. So we say the probability that x is greater than mu in a normal distribution, that is the probability p, x greater than mu. Let's label our normal distribution, right? This is the center, is going to be mu always. And if I want to find the probability that something is greater than mu, then I'm going to look at the area corresponding to bigger than mu. And this one we can just kind of do by eyeballing. If we know that's going to be greater than the mean, then the probability here is going to be 50%, or 1/2. As half the area is going to be above the mean, half is going to be below the mean. Which gives us our next example too. The probability that x is less than mu, the center, is also going to be 50%, or 1/2. All right, we're also going to think about not just with the mean, but we're going to talk about just a specific value. So let's say we have the mean in the middle. Let's say we had some value a over here to the left. The probability that x is greater than a is we're going to look at what is the area under that curve. Specifically, what is the percentage of the area relative to the entire area? So I don't know what that value is right now, but we can find it. We're going to see how to do that later on. But that's going to be the area corresponding to probability of x greater than a. The probability of x less than a is going to be the left side of that. So we're going to be finding that area. Note that these are related, right? So we could say that the probability that x is greater than a is going to be 1 minus the probability that x is less than a. This is our complement rule. And we know that the total area is 100% of stuff. So we think back to the previous page, we had 50% of the stuff to the left, 50% of the stuff to the right. Total, we have 100% of the stuff. Then we're also going to think about in between two values, A and B. So here, that area would represent this chunk. We could find this area. And in fact, one way that we could do that is we could break this up into the area less than A and the area less than B. We say that this probability here is going to be the probability that x is less than b minus the probability that x is less than a. We'll talk about why we want to use that in the next couple of pages. All right, that is if you take this big area corresponding to x less than b and you subtract off the part that x is less than a, then we're left with the area that we want to find. All right, so let's talk about now the standard normal distribution. We talked about there's lots of different normal distributions and they differ based on the mean and the standard deviation. Really, we're going to focus on the difference in the standard deviation. So here are 4 different normal distributions on one graph. So know that the first 3 we're going to look at all have the same mean, but different standard deviations. Let's talk about these really quick. So the first one in blue has a standard deviation of 0.4, and it's the smallest standard deviation. That means that more stuff is closer to the center. So that's going to be a stronger central peak. And as the standard deviation gets bigger, the yellow one is 2.2, there's less stuff in the center, but we still have a peak and it tails off at the end. It's still a normal distribution. Then we could talk about how the standard deviation or how the mean could change. So let's say that we shift the center to a different value, right? Then we can get a lot of different sort of things there as well. But it's not very useful to think about all these different normal distributions. We want a standard one to kind of compare to. And that's going to be the one where mu is 0 and sigma is 1. Centered at 0 and a standard deviation of 1. So we're going to call that our standard normal distribution, sometimes called a z distribution. And we're going to use z to represent the data point instead of x. So the good thing about a standard normal distribution is that all probabilities related to the z or standard distribution are known, and all probabilities of the form z less than z star, so that is just any number here, are given in a z-score table. So in this chapter, in this material, we are going to be using a z-score table to find probabilities. So let's talk about how this works real quick. So here is half of a z-score table corresponding to different z values. And these give us the probability that z is less than, insert that value there. So for instance, let's give some ones that we can kind of think about real quick. If we think about a z-score of 0, this is z equals 0.00, that corresponds to the mean, as we're centered at 0. And that's going to give us that 50%, 0.5 of stuff lies below that value. Let's look at another value just to kind of see how it works. Let's just pull out a random one kind of. Or let's say at the very opposite end, we have a z-score of 3.9, 3.09. That's how we read that. The probability that z is less than 3.09 is going to be 0.9990. And that should kind of make sense because the z-score tells us how many standard deviations away from the mean we are. So 3.09 is way out here. And if you think about the area less than that value, that is almost everything, almost 100%. All right, so we have all these probabilities. We're going to use these. Also note that we have negative z-scores as well. Right, z going from negative 3.4 to 0. So let's pull out one of these randomly. How about negative 2? Let's actually do negative 2.43. So the probability that z is less than negative 2.43 is 0.0075. Not a whole lot of stuff. We think about the picture here. Mu's in the middle, negative 2.43. It's going to be about there. And the probability that we're less than that value is about 0.75%. And we have all these values in between, but they always give us the probability that z is less than the value that we're looking at. All right, so we're going to come back to the z-score table to answer the next few questions. All right, so find the following probabilities using the z-score table. The probability that z is less than 1.25. First of all, let's talk about what that means. That means if z is equal to 1.25, we are 1.25 standard deviations above the mean. And that's because our standard deviation is 1. So we think about here is mu in the middle. Here's 1, here's 2. We're thinking about 1.25. And we're trying to find the area that we are less than that value. So we look at the z-score. We look at the z-score associated with z equals 1.25. So let's go back to our table and find that. We need to go to the positive part. So we're looking for positive z-scores. I'm going to erase this information so we can kind of start afresh. All right, so z equals 1.25. First, we look at the column, this left side of the column here, and we find our 1.2. Then we find our next digit, which is the 5. So this is 1.25. And we find the value associated with that is 0.8944. So we look at the first column, gives us our first two digits. The top row gives us our third digit, and we look at the corresponding value. So here we have 0.8944 is our answer. Note that that corresponds to 89.44%. So 89.44% of the area lies below 1.25, z equals 1.25. All right, let's do it again with negative 1.25. So again, we have mu in the middle. Here's -1, here's -2. We're looking at negative 1.25. We want to find the area that we are less than that value. So we're looking for z equals negative 1.25. Here we're going to go to the negative z-score table. Again, I'm going to erase this information so we can kind of start afresh. And we're looking for negative 1.25. And we're finding the corresponding value, which is 0.1056. So that tells us that that is the probability that we are less than negative 1.25. That is 10.56%. And you should think about, does the value make sense with what we're trying to find as well? That can catch some mistakes with more complicated problems. So let's do it a few more times with some more complicated things. Let's find the probability that z is between 0 and 1.25. So 0 is the middle, that's our mean. We have 1 here, we have 2 here. Here's our 1.25. So now we're just finding the area in between 0 and 1.25. So note that we can't just find the z-score for 1.25 because that would give us the total area. So instead what we can do is we can write this as the probability that z is less than 1.25 minus the probability that z is less than 0. That is this area less than 0. We can subtract off that big value. So we found z less than 1.25 on the previous page. That was 0.8944. We can look up on the z-score table, probably z is less than 0, but it's a special value. We should know that's 50%. So total, this is going to give us 0.3944 or 39.44%. So you have to do a little bit of calculation to get this special probability. We have to subtract off something. All right, next one, z greater than 1.87. So here we have 0, 1, 2. Now we're looking at a different value, 1.87. We're trying to find the probability that it is greater than that value. So the problem is that we don't want just the value corresponding to 1.87. That's going to give us the probability that's less than that. So we're going to use our complement rule here and write that this is going to be 1 minus the probability that z is less than 1.87. So this is what we need to find in our z-score table, because that's a probability of z less than something. So let's find that. go back to our z-score table. We find 1.8 on the left-hand side. We find our 7 on the top, and we look at our corresponding value, 1.87. Is this 0.9693? So using that value, this is going to be 1 minus 0.9693, which is going to give us a value of 0.0307, which is 3.07%. And here's a good example of looking at our picture and making sure this makes sense. It would be an understandable mistake to say that the answer is 96.93%. That's the value that we found for 1.87. If you think about the picture, that shouldn't make any sense because we drew a tiny little area that we're trying to find. That's definitely not 96% of the area. So use the picture to and some common sense to kind of make sure the answer makes sense. That will catch a lot of mistakes. All right, a couple more like this. The probability that z is in between 0.75 and 1.25. So let's draw this picture. Here's 0, here's 1, here's 2. So 1.25 we've drawn a few times. 0.75 is in between 0 and 1. So we're finding the area in between these two values right there. And to do those kind of in-between areas, what we do is the probability that z is less than the bigger one minus the probability that z is less than the smaller one. All right, so we've done this 1.25 business a few times. That was 0.8944. Let's find z less than 0.75 real quick. So go back to our positive z-score table. Here we're looking for 0.75 is 0.7734. .7734. We do this calculation real quick and we get 0.121 or 12.1%. All right, one more like this. We have 0, 1, 2, -1, -2. Here's 1.25. Here's -0.75. And our area is in between those. So we use our z-score table. We're going to find the probability that z is less than the bigger thing minus the probability that z is less than the smaller thing. We found before this probability, that's 0.8944. Let's go back to the z-score table and find our probability that z is less than -0.75. We go to our negative z-score table. We find -0.7 and the 5 here. And we get 0.2266. 0.2266, and we are subtracting those values. That will give us 0.6678 or 66.78%. All right, so a few more things here. Next kind of question is, what happens when we don't have a standard normal distribution, right? We have something with a mean and a standard deviation not equal to 0 and 1. The reason why we talk about the standard normal distribution is because we can convert anything into a standard normal distribution by computing a z-score. So the z-score is going to be our data point minus mu over sigma. And what this calculates is how many standard deviations above or below the mean our data point is. And that's what z gave us in the previous problems. When we have a non-standard normal distribution, we can use this formula to change it into a z value, and then we can use our z-score. And that's why we call it a z-score table, is because this thing is called a z-score. So this is a calculation that allows us to standardize our values. This allows us to compare different normal distributions and then find probabilities using the z-score table. So every probability related to normal distributions is known. We just have to translate it into a standard normal distribution first. So let's see this at work. The only difference between this problem and the previous problems is that we have to do a little calculation beforehand. All right, so suppose a population is normally distributed with a mean of 24.6, that is mu, and a standard deviation of 1.3, that is sigma. What percent of the data will lie between 25.3 and 26.8? So what we need to do is we need to find how many standard deviations above or below the mean 25.3 and 26.8 are. Note that we know the mean is 24.6. That's going to be the center of our distribution always. We need to find the 25.3, 26.8. So when we find our z-score, we have our x is going to be the data point that we're looking for. The mean is given in the problem, 24.6. And the standard deviation is the denominator given in the problem. So what changes from z-score to z-score is the data point itself. You do that calculation, and we get 0.54 for the first and 1.69 for the second. So these values, 25.3, 26.8, second one, we're trying to find the area in between those two values. But now we know that those relate to something in a standard normal distribution. Back in our previous problem, now we have the same thing we've been doing now for a little bit. We have 0.54 is our first value, and 1.69 is our second. So now we're thinking about this is the area in our standard normal distribution. So what we're really trying to find here is the probability that z is less than 1.69 minus the probability that z is less than 0.54. Note that that's equivalent to finding the probability that x is less than 26.8 minus the probability that x is less than 25.3. Note that's the probability that x is in between those values. Just as this is the probability that z is in between these values. But there's a way that we can find that probability with the z-score table easily. So we have two z-scores to find, 1.69 and 0.54. So let's go to the z-score table and let's find those values. Both are positive. Let's get rid of these markings. We can kind of start afresh. So we have 1.69, 1.6 on the left, 0.9 on the top. We go and find that value, 0.9545. And we also have 0.54, which will give us a 0.7054. So 0.9545, 0.7054. This is going to be 0.9545 minus 0.7054, which will give us a total of 0.2491 or 24.91%. All right, so what changed in this problem from the previous problems is we had to do some extra work at the beginning to find our z-scores so that we can do the same work we've done in the last few examples. It's an added difficulty to them. All right, the heights of a large group of people are assumed to be normally distributed. Their mean height is 68, and the standard deviation is 4 inches. So the mean is 68, standard deviation is 4. What percentages of people are the following heights? Taller than 73 inches. So we want to find the probability that X is greater than 73. We're going to translate that into the probability that Z is greater than something. We need to find the z-score related to 73. So we do 73 minus our mean, 68, divided by 4. So that's going to be z equals 1.25. So we're trying to find the probability that z is greater than 1.25. We've done this problem before. To find this area, we actually want to do the probability. This is 1 minus the probability that z is less than 1.25. And this was 1 minus 0.8944, which was 0.1056 or 10.56%. All right, so again, the difference is we need to find the z-score first to get this. And that's the percentage of people taller than 73 inches is 10.56%. All right, next let's do between 60 and 76 inches. So let's find our z-scores first. We have 60 minus 68 divided by 4 is going to give us a z-score of -2. And 76 minus 68 divided by 4 should give us a positive number. This will give us z equals +2. So what we're trying to find is the probability that z is in between -2 and 2. So that's going to be in our picture. This area. We can find it on the z-score table by saying this is the probability that z is less than 2 minus the probability that z is less than -2. So let's find those values. Let's go back to our positive z-score table. Let's find 2.00 is 0.9772, and negative 2 0.0 is 0.0228. So we have 0.9772, 0.0228. So 0.9772, 0.0228, which is 0.9544 or 95.44%. And this is where we actually didn't have to do this. We knew from our 68, 95, 99.7 rule that this is going to be about 95%. It's not exactly 95%, but it's 95.44%, but it's about 95% are within 2 standard deviations of the mean. So that could have been a shortcut in that problem. That would have been fine. One more problem to do. Let's read it and then we'll talk about how to do it. Tall Dudes is a clothing store that specializes in fashions for tall men. Its informal motto, which is a terrible motto, is our customers are taller than 80% of the rest. Assuming the heights of men to be normally distributed with a mean of 67 and a standard deviation of 5.5, find the heights of Tall Dudes clientele. So note first that we're given the mean, given the standard deviation, and we know that the customers here are taller than 80% of the rest. So we think about a normal distribution, which we have here. We have our mean is 67, and we know that the customers are taller than 80% of the rest. This is 80% of people are going to be shorter than the customers. So that means that we're trying to find this value. All right, so this is kind of going backwards here. Here we know what the percentage is. We want to try to find the z-score or find the x value. So we are going to first look up 80%. Note that's 0.80 on the z-score table to find our z-score. All right, so let's do that first. Let's go back to our z-score table. We want to find 0.8. So note that the z-score table is increasing. We start from negative 3.40 and we go from the bottom left to the top right. Those values are increasing until we get to, top right to the bottom left, they are increasing until we get to 0.5 here for the negative z-scores. Then we go to the positive z-scores and we increase the other direction, right? And we can just kind of follow that until we find our 0.8. So if you're kind of looking, we actually have 2 values that are closest, 0.7995 and 0.8023. And I think that the 0.7955 is closest. So that's going to correspond to a z-score of 0.84. Note that you could use z equals 0.85, or you could do in between if you really wanted 0.845. Any of those answers would be fine. We're just going to try to find anything in there would be great. So here we know that we are associated with the z-score of 0.84. That's what we'll use here. But we want to find the x value, the data point with our normal distribution. So we know that z is going to be equal to x minus mu over sigma. Now we know z, we know mu, and we know sigma. So we're just trying to find our data point x. We're going to have to solve that equation for x. We can do that by multiplying by 5.5 on both sides. That'll give us x minus 67 on the right and 4.62 on the left. And then we can add 67 to both sides. And we'll get x is going to be equal to 71.62. So find the heights of the tall dude's clientele is the question, right? The clientele is 71.62 inches tall or taller than 71.62 inches. All right, so that's kind of going backwards to this process. Given the probability, find the z-score, and then maybe do a z-score calculation. All right, and this concludes all of the material for statistics, kind of a big thing right here at the end with normal distributions, and concludes all the material for the course.